So welcome everyone. So in the 1-minute papers for the previous lecture, we had some comments. So one of them was asking to re-explain fin. So let's have a go at it. Instead of redefining everything from scratch, I've imported some definitions that we can reuse. So the syntax might be a bit different. So for vectors, for instance, I think we call them vect with a T. This time there's no T. And the cons is also a different one because it's from the standard library rather than the comma dash we've been using. So rather than importing the fin, because that's what we want to have a look at, I'm going to define it. So remember that fin n is supposed to be all of the numbers that are strictly smaller than n, a good representation of them.
Or all n of them.
So if we have a 0, then it's a valid fin only if the upper bound is non-zero, because it needs to be strictly smaller than the upper bound. So that's why we give it a type of the shape suc of something. We don't really care what the something is. Here it's an abstract, an arbitrary variable. And then that's the tricky bit. So the idea, it's shown here below where we are trying to list all of the fins with an upper bound of 4. The idea is that you can describe the fins for a non-zero upper bound by saying, okay, I have 0, and then I also have all of the ones that have an upper bound that's strictly smaller by 1 shifted to the right. So this is where we're saying, okay, all of the numbers smaller than 4 are 0, 1, 2, 3, and we can see that as 0 and then mapping 1 plus, so suc, over 0, 1, 2, which are all the numbers strictly smaller than 3. And so this is what gives us our type for suc. Basically, we're saying we're happy to take any of these numbers that are smaller than n, and that will give us a number smaller than successor of n.
Yeah. So the idea is that to make the next finite set, you take the old one, you successor of everything, and then the new 0 comes in at the bottom. So let's draw a picture of that. So let's see. You can let's see if we can just build elements of finite sets.
Yeah. So the first thing we wanted to have a look at is fin 0. So here the type should actually tell you that something is going to happen. Oh.
I mean, why not just try and build an element of fin 0 just to see?
I mean, we can try, yeah. So if I use Control-C, Control-R, I'm telling Agda to refine the whole with any constructor that would work. And here it tells me that no introduction forms were found. And that's because if you look at the type of the constructors for fin, the return types are always the successor of something, because as we said, we need an element that's strictly smaller than the bound, and if the bound is 0, there's nothing that's strictly smaller than it. So that's why if we try to actually build a fin 0, it doesn't work. And even better than that, we can prove that there are no such elements. So we can actually build this function from fin 0 into an arbitrary type A, proving therefore that having a fin 0 is basically absurd. And we do this using the absurd pattern saying like this is absolutely impossible. And then under the hood, Agda will look at these constructors and see, yeah, indeed, you cannot have a fin 0.
Yeah, no case to answer it.
Then if we try to build an element of fin 1, well, we can actually ask Agda to list all of the possible solutions it can think of, or at least the first few ones it can think of. And here it only comes up with 0. And that makes sense, because if you think about the characterization I've given, whereby if you have a fin of a non-zero upper bound, you can have 0 plus suc of any of the smaller ones.
Yeah.
So
So this in particular is the 0 where little n is 0. And if you fill in, you can put suc in that hole, but you then have a problem we saw earlier.
Yeah.
If you want to make an element of fin1 with suc, that reduces your problem to the, slightly challenging making an element of fin 0. Right, not going to happen.
So the only possible value here is going to be 0. And then we have the same with fin 2. We can try to ask ACTA to fill in the hole. And this time we get 2 possible solutions. So we always get the 0, because as long as the bound is non-zero, it gets thrown in. And then we can get the suck of anything that was of the fin n-1. So in this case, fin 1. And we saw that in fin 1, there was exactly one value, which was 0. So we get 0 and suck of 0. Let's just pick an arbitrary one. Of course, it picks 0. It's going to pick 0 every time. And we can do the same again for fin 3. Where this time we get 0, 1, and 2. So then if you want, you can try to build this function called old fins that will take the upper bound and then give you a vector of n value corresponding to each one of the fins that you've seen. And this is basically the definition, more or less. So here we've instantiated it for n equals 3, for suck of n equals 4. And you can see that using the scheme we've described, where you always throw in 0 and then you shift all of the smaller ones, this is already sort of an inductive definition.
Yeah. This is the thing that's slightly counterintuitive about fin. We all go through this process. Is this kind of way they build the numbers going in this sort of diagonal pattern, where elements of fin 3 are built from elements of fin 2, and so on. And it's a little bit tricky to get your hands on just one of these columns, like all the things in fin 3, because they're not made from other things in fin 3. They're made from things in fin 2. So what Guillaume is saying is, how do we get our hands on these columns? How do we generate all the fins in fin 3?
So that, yes. On fin 3, we do like that.
Yes. Or fin 4.
It as suck of fin 2, and you can really see that those are not the same. Like
Yeah.
fin 2 from here is the suck of the fin 2 from the other columns, right? You can also put the index right in fin 2 for the inner end, right?
Yeah, so this n here is introduced by the variable block, right? So it's automatically introduced as an implicit argument, but we can always fit in the implicit arguments explicitly by using the named application syntax. So here I can say, using the curly braces to say named application of this implicit argument, name it. And then in fact, it's completely unambiguous, because you can see that the upper bound here must have the shape suck of n. So n must be 1 minus the upper bound that comes n from the type annotation on the outside. So here I can even just say press Ctrl C, Ctrl S, which will solve all of the holes that are uniquely determined by all of the constraints that are in scope. So it's not like Ctrl C, Ctrl A that does proof search. This time it's only looking at the constraints and seeing what is already solved. So here I put in a hole, but there was no need for me to actually fill in this value, because it could be reconstructed automatically. And here it's the same, it can be solved. And here in the suck case, I can also introduce it, and it can be solved automatically.
And then you can see in which quadrant it fits in the board, right?
Yeah, exactly.
So fin 1 is the top left, fin 2 is
Fin 2 is
top.
fin 2 is another 0, so it's going to be this one, and then fin 3 is going to be this one. So yeah, there was another question. So someone asked for the formal definition of the lookup as a decision procedure. So the very advanced lookup that we had at the end that we rushed through and didn't define. And my advice would be to try to define it yourself. And if you're struggling, you can always ask in the lab to get some help. But I think the fact that it's a decision procedure, that you need to analyze recursive calls and patch up the types on the way out after performing the recursive call is actually a very interesting thing to see. And it will be better if you did it on your own than if I just like throw the code at you. All right. And then we can move on to this content. So maybe I'm going to try with the easy ones and then I'll pass the relay to Fred. So today yesterday, we had a question about the difference between proofs and programs and functions and proofs and functions and statements and types. And this is what we're going to see today. Basically, the fact that in Agda they're the same thing. You manipulate them using the same construct, and then it's only your point of view on these things which determines whether it's a proof, which is usually you call something a proof when you don't really care about its contents computationally, and you call something a function where the computation actually matters. So our first, perhaps naive approach to proofs and statements is to say, well, every statement is either true or false, so we can just model it with a Boolean, and then we can introduce the usual propositional operators as operators on the Booleans. And so, for instance, we could say, well, if I have a proposition A and I have a proposition B, both of them represented by their truth value, so by a Boolean, I can say what it means for both A and B to be true by defining the A and B function. So here I haven't added the comment, but it's on the lecture notes where basically you go back to CS106, you dig up the old truth tables, and you just implement it by pattern matching on A or B or both. And that gives you this encoding of conjunction. The problem, of course, is that when you start talking about not just two things being true, but countably many things being true, like the fact that full n a natural number, maybe I should write it this way, P of n holds, then suddenly it's a lot harder to write this as an encoding into Booleans, right? Because what would it look like? So it would be something like this, where you have a function from nat to bool, and then you need to return a single Boolean.
It's a
Oh, it's a
keyword.
keyword. Well, let's. Okay.
Can we put the error bar down? Like, I can't see through it.
Okay, yeah, we can do that.
Oh,
I have put this picture of this board on that note already.
oh cool. Right, so here, I mean, we could say it means that P of 0 is true and P of 1 is true, and well, it's going to be hard to go all the way to the end, right? So then maybe this encoding is actually a bad encoding of what it means for a statement to be true, whether like we can actually give a Boolean back. So the idea then is to, instead of talking about Booleans, telling you whether something is true or not, is to talk about what a good proof of a statement is. And then statements are going to become types, and then the proofs are just the evidence that the type holds, that the statement is true.
So I don't know if you remember in CS106, I was very careful to lean on the fact that Boolean logic was about things we could test, about whether there was 5 volts or no volts in that wire. And Boolean is the type of test results. But what if there are things we can't test? We can't try all the numbers. Then we need to start talking about evidence, and maybe the Boolean thing is not such a good idea. And usually what would happen back when 410 was a semester 1 class would be I would be giving the first years the lecture about truth tables and Booleans, and then going straight to another lecture room where I would explain to the 4th year why it was rubbish. And this irony was crippling for me. Hence, hence all of that heavy leaning in first year about testability.
Right, so we're going to look at various proof derivations, and so just to remind you a little bit what these look like. So all of the rules will look something like this, where at the top you have a bunch of hypotheses, and then you have this ASCII art rendering of an inference rule, and at the bottom you have the conclusion. And so all of the rules will be spelled out that way. And I'll just do the two first ones because they're really easy. So the first one is the true statement. It's always true. And here we can define it using a record with a single constructor and no fields whatsoever. And so if you ask for a proof for it, well, I mean, I don't even need to give it. I think Agda is able to just figure out that this is true. Because a constructor is the collection of its fields. There are no fields. It's really easy to build. So there's nothing really interesting we can do with it. It's just really useful to just say that something is, for a fact that something is completely true. So if you want to, well, maybe we'll see later if we can define some propositions this way.
Should we stop a little bit here? So this is this confusing thing where the underscore on the left here means I don't care. I'm not even going to name it. The underscore on the right means Agda, you figure it out, right? So it's not the same underscore.
Yeah, on the left it's the name of unit tests essentially, and on the right it's the name of stuff.
Fill it in for me.
That should be done automatically, right?
Yes. And Agda's strategy for filling in a record value is to try and fill in the value for each field in turn. And that's over very quickly.
Mm.
Right. So the point is, this is the record with no fields, right? So it's really easy to give values for all the fields in the record with no fields.
Yes.
It kind of corresponds to
Yep.
fulfilling all the hypotheses above the line here, right?
All right.
How is this different from the unit type?
Oh, it is the unit type. Yeah. Yeah. So that's how we model like the ground truth essentially. And then we have.
Yes. We should apologize for the fact that in Haskell, empty parentheses means the unit type and also the trivial value. Whereas earlier we saw the empty parentheses on the left-hand side of a program, meaning that's impossible.
No.
So sorry about that. That's one kind of big notational change from the Haskell world, is that empty parentheses mean exactly the opposite of what they used to mean.
So then we have the false statement. We saw the one that was always true. Now we are going to see the one that's never true. And it doesn't come with any constructor, so there's no rule with bottom as a conclusion. You only have an elimination rule, which is like the principle of explosion, telling you that if you happen to be able to construct a proof of bottom, then you can prove basically anything, because it should be impossible. And this is defined not as a record, because a record is a collection of its fields, so a record with no field is always full, but as a data type with no constructors. And this time, because there are no constructors, there's no way to build any value in that data type. So again, it's a bit tricky to see that the record with no field is actually always, you can always build it, but it's the opposite for the data with no constructor. And then I can build this X file. So principle by using the absurd pattern, because as we said, there are no constructors for bottom, so there's no way you could get an argument of that type. So you can just dismiss it this way.
It's maybe helpful if you introduce an X on the left and pattern match on it.
Yeah, I can try to do it interactively, and Agda should just tell me, yeah.
But what's the purpose of defining X false if we're not going to ever use it because we can't ever get the empty type?
Right, so yeah, my mistake. So I said we could never actually get it, but we can never get it in a closed context. But we could always have it because we went under some assumptions and they're contradictory, and therefore we come up with like an actual proof of false. But the proof of false is demonstrating the fact that this branch is completely dead code because the set of assumptions are contradictory, and therefore we will never be able to actually enter it through computations. So
like
it-
the use case is understanding that you made a mistake somewhere because you have two contradictory assumptions.
Yeah, I don't know if it's a mistake, but yeah, basically it's a branch that is impossible.
Well, so you've been asked to deal with a situation which can't happen.
Yeah.
So someone is lying to you, and you need to tell them to go away. That's
Yeah.
the situation that shows up. They're demanding that you produce a value of type A, and instead of actually ponying up this value of this type, you don't even know what the type is. Instead, you say, "Stop lying to me." So you get situations where it's about escaping from situations, from hypothetical situations that are actually impossible. If you've seen Bedazzled, this is the bit where Dudley Moore blows a raspberry because he doesn't want to be in that situation anymore. But maybe that's a 1960s movie.
So for example, maybe you have a better example.
Yeah, so for example, someone is asking you to prove A, but giving you assumptions which are contradictory, then you're like, stop lying to me and dismiss the whole question, basically, right?
Yeah.
Okay.
Yeah, or maybe a typical example would be to do the same test twice, and then having different answers. And you know that if you test whether a number is smaller than another one, no matter what the answer is, it should be the same all the time, right?
So for example, you could prove that every natural number is either smaller than 5 or equal to 5 or greater than 5, right? And now you instantiate this to 14. Then your proof is going to say that 14 is either smaller than 5 or equal to 5 or greater than 5. And in the first two cases, you can show that this is impossible, right? So you can only focus on the last case. But your proof will still say, okay, maybe it's the case that 14 is smaller than 5, and then you say, that's ridiculous. I don't have to consider this case, expulso, right?
If you want to do implication.
Should I do implication?
And I think then we'll have some interesting cases of
Yeah.
proof of false.
Okay. So implication, I'm not sure how I should read this. So if I want to prove that A implies B, then what does this mean? Well, I can assume that A holds, and then if I can prove that B holds, then I have proved that A implies B, right? It's kind of the constructive reading of what it means to say that something implies something else. I assume that the moon is blue, and then I derive that blue is the moon, or whatever. And so that's how I introduce A implies B. I just show B, but I get to assume that A is true. And if I know that A implies B, how do I eliminate it? How do I get out of it? Well, if I have A, then I can get a B, right? So I know that A implies B, I know that A holds, hence B must hold, right? All men are mortal, Socrates is a man, hence Socrates is mortal, right? So this looks a lot like how you write a function, because it says to write a function from A to B, I assume I have some inputs of type A, and then if I can produce an output of type B, then I have a function from A to B, right? And if I have a function from A to B, and I have an A, then I can apply the function to that A and get the B out, right? So I can model the implication as the functions, which I think is what's happening down here. Right, so we see here we have the fancy Unicode arrow, which is the same as the Unicode function space, right? And here is application, saying if I have a function from A to B, and I have an A, then I get a B, and it's realized by just function application. Okay, so right, should we restart this?
No, I forgot to remove it.
We got
Sorry.
international keyboard consternation.
Okay, so it should be the case that A implies B implies A, right? So if I know A, and I know a B, then I know A.
Hidden information. Arrow groups to the right.
Right. So this really means this, right?
Mm.
If it grouped the other way,
You'd be in trouble.
then can you see how to prove this? I can't, right? So this says if A implies B, then A must be true. One thing that implies B is if this was false, right? So if false implies B, which is true, then false. So that's not a good way to group it. But if you group it like this, then this says, well, if A is true, then I have to show that B implies A, right? But A is already true, so I don't particularly care about if B is true or not, right? But okay, I could do this slowly. So I want to show an implication, and we had a particular way of showing implication, which was this introduction rule, right? To show A implies B, I get to assume an A, and then I have to produce a B. So the canonical way to do that here with a function is to say lambda A goes to something, right? Because now my goal is B implies A, and I have assumed one additional fact, which is that I have a proof little a of A, right? And my goal is still a function type, so I can do another lambda. Okay, so now my goal has turned into A, but I have assumed one more thing, right? Okay, and then in this case, I can just use the assumption A like this. So I'm just introducing some lambdas and returning some values, and that's how I build up my proof, right? Right, and then after the fact, if I want, I can say, okay, I can actually put this in one lambda that introduce many things. Okay, I'll do a negation as well, maybe. So negation we can see as a special case of implication. To say that not A is true means that A implies falsity, right? So not A is true if A is as true as false, right? If A is true, then false is true. And a way to see how you can eliminate this is to say, well, if you have not A and you also have A, then you get anything you want, right? Which, if you read it like this, if you have not A, so you have A implies false, and you have A, then you get falsity, and then from falsity you get anything you want, right? Right, so I guess we should define this. So that's \neg for neg. A equals something. And we say that's A goes to bot. So that's how we form the type. And here's absurd, which implements this rule, right? So it says if I have not A and I have A, then I get whatever I want. Okay, so I'm trying to introduce a function type, so I can take two arguments. I have not A and I have A. Oop.
There's a gratuitous activism which you ought to explain.
Yes. So there's many fancy Unicode symbols here. So there's the lambda for the lambda, there's the arrow for the arrow, and then it's hard to choose names, right? This is one of the hardest problems in computer science. So a typical way to do it in Agda, because we are allowed so many Unicode symbols, is that we take the name of the type, but we convert things to lowercase. So if the type is called big A, then I typically call the variable little a. And then I can just remove all of the spaces here in the variable name, because I'm not allowed spaces in the name. That's one of the things I'm not allowed in a name in Agda. Right? So I take the name here and I kind of convert it to lowercase and remove the spaces. And then I don't have to think too much about what I should call it. But of course I can call it whatever I want, right? And I want to call it not little a.
And you can see from the color, this is just one purple thing. This is nothing special. It's just a name that Fred has chosen to remind him what it means.
Yeah.
Right? It's
So-
not doing something.
It helps a little bit if you're brave enough to read Agda code rather than write Agda code, in that you can kind of see what the type of this might be just by looking at the name. But I wouldn't recommend it. It's much easier if you can ask Agda about things. Okay, so I've introduced things with a lambda. Now I have to produce a b. Okay, that looks hard because I have nothing to do with b here. But I can, so this is what Agda tells me if I just ask about what I have in my context. I can also do control U, and ask again. And then Agda will normalize things as much as possible here. So before it said neg of a here, right? Now it said, well, neg of a is actually defined to be this, so it wrote that out explicitly. So now we see that actually I have something which implies bottom. And further up we defined x falso, which goes from bottom to anything you want, right? So maybe here I can do x falso of something. So now all I have to do is produce something of type bottom, and we're golden, right? Shouldn't be too hard. And thankfully it's not, because we have something that produces something of type bottom in our context. So if you take this neg of a and apply it to something, then we get something of type bottom. Okay. And now all we need is an a, which is exactly what we had. Right? So we do get this absurd rule that we can't have not a and a at the same time. Or if we have not a and a at the same time, then we have everything. Right? Your favorite b. Proof of p equals np, or what have you. Okay, so I guess we'll do this as well.
Sorry.
Yep.
What was dollar sign again? Is it conjunction?
So dollar sign was how we defined application.
Yeah, but you could simply you could simply remove it
So in this
Yes.
case, yeah,
because it's just a function.
yeah. I just wanted to use the things we defined above, right? But it's like the Haskell dollar sign for application. Yeah. Okay, let's do one more. So what is this? So this says that if I have a, then I have not a, right? So if a is true, then it's impossible that not a is true at the same time. And we could try to do this. So I introduce an a. Oops. Okay, so now we have to show not a. And I guess we can fully normalize this. So we see that that's actually defined to be a implies bottom, and then all of that implies bottom. So this time it's bracketed to the left, right?
So you did it to normalize?
So that's something you can do in the middle of the night after you do it long enough. It's control U, and then the thing you want to do. It's an Emacs thing. So control U modifies what the command means. And it's twice because there's also a simplified mode that doesn't work most of the time. So control U, and then what you want.
So it's control C, control comma for what's going on, and then control U, control C, control comma for what's really going on. Yes.
Okay, so we see that the goal is again a function type. So we can introduce another lambda. Okay, I'm going to call it neg a. Okay, and then our goal is bottom, but what's really going on? Well, again, I have a function that gives me what I want if only I give it that argument. Right.
Right, or you could use absurd also.
So I could do that, and
With it
then
normally.
after I've done that, it looks like this is very similar to absurd, right? So in fact, all of this is just absurd.
Oh,
isn't it?
no,
Not quite.
no.
It's backwards.
Yes.
Okay.
Flip absurd.
Flip of absurd. Yeah, okay. So let's maybe not do that. So we see that if a is true, then not a is also true. And you could think, okay, I know that this is the same, so maybe I can go the other way. But I would invite you to try and do that. And you see that it's not as easy as you think. So here you're saying it's impossible that it's not true, but that doesn't mean that you have evidence that it's actually true, right? It's impossible that, I don't know what, there are no twin primes. Doesn't mean that you can actually find two twin primes. Okay, I don't know.
I guess that's the point here, where the stakes have been raised from the logic we had before. So not A means you can't prove that there's no such thing as an A. But to deliver a proof of A, you actually have to build one. We're actually talking about computability here. So things which are kind of impossible, things which are beyond reach of computation aren't going to be provable, even if somehow there's a sort of magic reason for believing they have to exist. How'd you get your hands on one?
I'll maybe jump back in because there's a lot of Unicode. So. Let's see. Okay, we have 10 minutes, maybe 5-10 minutes. We won't have time to go through all of it, but I mean, you've seen the principle, right? So you get a bunch of rules. Some of them are introduction rules. They turn into data definitions, basically, or aliases for implication. And then you have elimination rules, which turn into top-level constants that you can then use, combine with other top-level constants to build proofs, like the double negation one. So for conjunction, the introduction principle is like, well, if you want to prove A and B, you better have a proof of A and a proof of B. And you combine them, and that's how you get the proof of the conjunction. And then we have these two elimination rules telling you, well, if you have a proof of both, you can get a proof of either by projecting out the one you're interested in. And so, as I said, the introduction one becomes a data declaration. It could also be a record, but because there's no choice, but for change, I picked a data one. So what does it mean to have a proof of A and B? Well, you better have a proof of A and a proof of B, and then that gives you a proof of A and B. And then I can have the two elimination rules that we talked about earlier first. And they're going to extract, or I should probably do it interactively, right? So if I look at this, in scope I have this proof P of A and B, and I want a proof of A. So the only move that I can make is to actually inspect what my proof looks like. And because A and B is defined as a data type with a single constructor, I'm going to get a single clause with a match, with a pattern matching that constructor. So it's picking horrible names, of course. So actually, let me name them here to trick Acta into using good names for the next one. So now I have this comma constructor with a proof of A and a proof of B, and I wanted a proof of A, so I can just return the first component. And I can do the same for second. So I have a pair. There's nothing else to do but to split on it. I get these two things, and then I return the appropriate value. So this is where we start to see that proving and programming is basically the same, like this first and second projections. You've used them all the time in Haskell, and now they show up as inference rules for like the small proof calculus. But they're just normal functions in Acta. And they're actually useful functions. Okay, and then we can define the swap function, or rather the proof that if we have A and B that holds true, then we can prove that B and A also holds true. And here I'm not going to use pattern matching on the left or anything. The idea is really to reuse the proof combinators that we've defined above that are manipulating what it means to have a proof of one or the other and construct derivations this way. So Lambda abstraction is the introduction principle for this implication. So we grab the proof P that A and B holds true. Then we need the introduction principle for the pair, and that's the constructor to the date type. So you can just use the comma. And then here we need to build an a B, and here we need to build an A, corresponding to each one of the projections of the pair. And for that, we can use the elimination principles we've defined above to extract the proofs we're interested in.
Yep.
Then there's disjunction. So, yeah.
It's a small thing, but I see quite often that you use the syntax where you define like lambda and arguments instead of like defining the parameters before the equal sign.
Yeah.
Why is that?
So here it's really because I'm thinking of swap as a proof that A and B implies B and A. And so I only want to use the introduction and elimination principles for these logical connectives. But you could just as well write it on the left. So this first and second here, I introduced the argument and pattern matched on them on the left, because I was defining these sort of core principles corresponding to this proof principle that if you have a proof of A and B, you have a proof of A, and you have a proof of A and B, you can get a proof of B.
I would go slightly further and say that in general it's a good idea to introduce them on the left rather than on the right. It's more readable and it makes more sense. So it's
but here, because we're mostly talking about proof, the idea was really to have this to introduce basically the encoding of the logical notions first, using the language constructs, and then purely work in the encoding without relying on the language itself.
Yeah, so I think it's just a formal game here, is that kind of there's a dividing line here where, first of all, we're showing that we can realize these rules, and then we're saying, okay, never mind how we realize the rules, show that using these rules we can make this deduction. But yeah, under normal circumstances we wouldn't be quite so fussy, and we would just pattern match on the left.
Yeah, it is actually quite often a better strategy to stay on the left and match as much as possible. So for disjunction, we have two introduction rules. If we have an A, we can prove A or B. And if we can prove B, then we can prove A or B. So that translates into a data type with two constructors. So we can say, if I have an A, I can prove A or B. And then the other constructor will tell me if I have a B, I can prove A or B. And then the elimination principle, well, it's always acting as a mirror of the introduction rule. So if you're saying, well, I could have built it in these two ways, then to eliminate a proof of A or B, you need to be able to handle the two possible sources of an A or B. So here, if I have a continuation taking an A and giving me a C, and if I have a continuation taking a B and giving me a C, then from an A or B, I can always construct a C.
So you can think of this as saying, whatever it is you're trying to do, so C stands for what your problem is right now. If someone gives you A or B, what use is A or B to you in your attempt to solve whatever the problem is that's in front of you? And yeah, it would be very useful. A or B would be just the thing you needed if you knew that you could solve your problem given A, and also if you knew that you could solve your problem given B. So the sort of abstract nature of where the hell does C come from is often the mystery, but it's no mystery. It's whatever you're currently working on. When someone says, here, maybe A or B is useful to you. This is just saying, how is A or B useful with the problem at hand?
And so we can realize this eliminator as the thing called case here. So I've introduced P for the proof that we have A or B, and then L and R for the left continuation and the right continuation. And if I case split on P, it will give me the two possible introductions, and of course it's again picking horrible names. So if you actually name the arguments in the type of the constructors, I will tend to try to respect that. That's why I always do it too late, but do it anyway. So in this case, we discovered that the proof of A or B was built using a proof of A and the first inference rule. And therefore, to construct the C, we're going to disregard the continuation taking a B and just apply the one taking an A. And the converse for the other one. If we build the proof of A or B using a proof of B, then we can use the continuation that consumes a B. So we've realized these inference rules, and then we have time just for one example. It's a bit of a tricky one. You can think of the other ones that might be true too. It's this distributivity law that says that if you have a proof that A and B or C holds, then you should be able to construct a proof that A and B holds, or B or A and C holds. So what this name is saying is that AND distributes over or from the left. And so you can have the equivalent from the right, maybe other rules too. And again, I'm going to construct it purely on the right-hand side because I'm trying to use all of these inference rules rather than working in ACTA itself. So I have a proof, and then I could decide to go on the left or on the right here, but I could also try to gain some information from the proof I just found. And there's no way for me to decide whether I want to build a B or C, because in the context, I have either a B or a C, but I don't know yet which one I have. So the proper move is probably to start by inspecting this one to tell me, which will tell me on which side I need to go then. And luckily, we just defined something to inspect this side, so I can do case on the second component of P. And here I've written a partial application of case. So if I use Ctrl+C, Ctrl+R to refine the goal, it will automatically fill in like the missing arguments so that everything is all types. So I have two cases to consider. The first one is this one, the continuation that takes an A, and the second one takes a B. Okay. Of course, here they're renamed, so they take a B and a C respectively. This is not going to throw in the parens. Oh, it did. Okay. So in the first branch, I just got my hands on a proof of B, and now I need to pick a side. Well, I'm not going to pick the one where I need a proof of C because I don't have one. So I can go on the left here, and then I'm using the introduction rule for conjunction. And I need a proof of A, which I can extract from the proof of the conjunction A and B or C by taking the first projection. I don't know why I get parens.
So it's the crucial thing here that when you're building a value in this type, you have to pick this constructor or that constructor, which means you have to deliver one computable bit of information. But fortunately here, this is packing up one very useful bit of information, namely whether this was the B or whether the C. So this, so we're really looking at one bit of information coming from the input to decide which bit of information to give on the output. And that's the sort of ordinary logic we taught you earlier in your degree wasn't paying any attention to whether the bits were computable.
Right, so I built the A, the B was just passed to me so I can fill it in, and here it's going to be the mirror, right? I got a C, so I'm not going to try to build a B. I'm going to go in the second component of the sum. And this time I can once again extract the A from the initial pair and then return the C that was just given to me. Right, and so this is a useful distributivity principle that we can implement purely using the inference rules. So, okay, so then there's we don't have time for it, but you might have seen like this decidability thing in the coursework, and next time we'll look at it in more details.
Right. So that's the thing. You might have encountered the law of the excluded middle, the thing that says either A holds or not A holds. Well, that's no longer always true for us, because it doesn't just mean God knows one way or the other. It means we can actually tell. We can, we can compute which of the two possibilities it is, and that. So the law of the excluded middle, read computationally, says there is an oracle which will tell you the truth or falsity of any statement, and that's really quite amazing if true, right? It really is promising far too much. It's really saying, I know the answer to every question. That's what the law of the excluded middle is promising you. So of course you can't prove it. However, we can carve out, we can talk about which things really are decidable. So, but that's not something that you get for free. So to say that something is decidable, you mean we have a way of using computation to tell whether this is true or false. And that's really useful information to know that there's a computational way to tell whether something's true or false. So that's key thing to pick up next time.
All right, I'll stop the recording.